Hello everyone, in this video I'm going to be talking about 4+2 cycle addition reactions, also called Diels-Alder's reactions, and I'm also going to be talking about dienes, dienophiles, and eventually I'll talk about their regioselectivity and the stereochemistry of those Diels-Alder's reactions. So before we start, I want to do a little bit of background on dienes and dienophiles and what dienes are reactive and what dienophiles are more reactive than the other ones. So let's first take the examples of these conjugated dienes. And anytime you have a conjugated dienes in the S-cis form, they are reactive toward Diels-Alder's reactions, like we have in this particular case. It's 1,3-butadiene, or I have this cyclic five-membered ring where I have two double bonds inside the ring conjugated with an oxygen. Instead of an oxygen, you could have something else as well. I could have R groups or the substituents on these dienes, and that will make them more reactive. So presence of these R groups right there, that will make these guys more reactive. You can also use these cyclic dienes as well. So these are various examples of dienes we have some symmetric, and some of them are unsymmetric dienes. For example, this one is symmetric, that's an asymmetric diene, but when I look at the next one, it's an unsymmetric diene, which technically means the both the bottom and the top side are not really the same in this particular case. So for these 4+2 cycle addition reactions to take place, they must be in an S-cis form instead of an S-transform, even though the S-transform is going to be more stable, but they can rotate by in a single bond, and I'll show you that in a minute. To make those more reactive, I have to have some R groups or some alkoxy groups and even alcohols attached to them. So the presence of OR or OH or R will make them more reactive. And I do have some of these examples already there, like this one. If I compare, let's say, call this 1, call this 2. If I compare between 1 and 2, 2 is more reactive because of the presence of an electron donating group. So at the end of the day, presence of an electron donating group will make these dienes more reactive. And even some of these cyclic dienes are even more reactive than the non-cyclic dienes. For example, if I compare between this, let's call this A and B, between A and B, this B is going to be more reactive because it's in a cyclic. And also, in addition to that, there is a lone pair on those oxygens, and that can have a resonance in with those conjugated dienes, making those carbons even more electron rich. Because in these reactions, the dienes will act as an nicophiles, and the other guys will act as an electrophiles. In the first arrow, everything takes place in a concerted step. So typically, you don't really have a specific nickel-phile electrophile, but in the first arrow, you see where the positive charge is going to be and where the negative charge is going to be, or at least where the most partial positive charge is going to be and where the most partial negative charge is going to be. And I'll show that in a minute. So eventually, um, these guys will exist in an S transform to be more stable. Except if it's in a cyclic form. If it's in a cyclic form, they're always going to be in the S-cis form. Like this is always going to be in an S-cis form, so that's why this is more reactive. This is in an S-cis form, that's why it's more reactive. But if it's in an open chain, they will exist in an S-transform, but you want to make those in a S-cis form, and there is an energy cost of 12 kilojoules per mole. Another way of saying this, S-transform is more stable by an energy factor of 12 kilojoules per mole, but you can easily convert those by just a single bond rotation. All I really got to do is just rotate this bond, and I will be able to get into the S-cis form. So once it's in an S-cis form, that's when it's ready to do these 4+2 cycle addition reactions. Now, there are some guys that are going to be always in the S-transform. And if they are in the S-transform, they are going to be not reactive toward Diels-Alder's reaction. Like this one right there, that's in a S-transform. So is this one, and so is this one. Well, I can't really convert these first two because of the restrictions with the ring. So since I can't really convert those, they're not gonna do Diels-Alder's reaction. But if I look at this next one, this is, all right, so I have this one a little bit not in the right position. So this particular S transform, if I try to convert it to the S cis form, let's see how that's going to look like. So I can just copy this down. And when I copy this down, this is how it's going to look like. And I can just move this a little bit further. And when I move this, this is how we'll have this. Now, the problem with this S-cis form is there is too much steric hindrance because of these bulky grips. So this particular compound is going to be less reactive than the first one that we have here, the 1,3-butadiene, because of the energy cost to convert this particular guy into an S-cis form is going to be a lot higher than the energy cost to convert this S transform of 1,3-butadiene into the S-cis form of 1,3-butadiene. So that way, based on that, you can actually tell which ones are going to be more reactive and which one's going to be less reactive. So remember, some of them will have restrictions where you can't really convert them in as cis form. As a result, they're not going to be reactive toward Diels-Alder's reactions. The next thing you need to have is the dienophile in this case, and the dienophile is what really is going to be having a positive charge or a partial positive charge in the beginning or in the first arrow, and they usually are they work well if you have an electron withdrawing grips on them, and that makes those more electrophilic. And some of the really good examples are obviously going to be, you got an alkene or alkyne, or you can have an alkene that's unsymmetrical, or you can have an alkene but then you got these electron withdrawing grips on them. So I can see different varieties of electron withdrawings. I can have in cis form, I can have in a trans form. That's completely okay. And then if I have an electron withdrawing group, it pulls the electron density from that pi bond between the two carbons, and as a result makes one of those carbon very electron deficient, and as a result becomes very electrophilic through resonance. And how does that really work? So suppose if I take this as my example, and if I go ahead and try to do the resonance on it, I can have this one moving down here, and I can have this one moving down here, and as a result I'll have another resonance structure where I got a negative charge on the oxygen and I got a positive charge on that particular carbon. So having a positive charge, or even with one of those resonances, it makes that carbon very electron deficient and act as an electrophile. And as a result, the dienes, most electron-centered carbon can attack on this particular electropositive carbon, doing the initiative of these Diels-Alder's reactions. So Diels-Alder's reactions are actually concerted. You have three arrows going on, and they all going to be taking place in one step. So let's look at this particular example here. So I got this 1,3-butadiene, and obviously this is in a transform, and I don't really need that in an S transform. This needs to be converted into an S cis form so that you can see this better how it's going to work out. And this is an S cis form, and I'm going to align my dienophile into a vertical direction as well so that I can easily see where the arrow is going to be uh, moving. So I start from, right now it doesn't matter where I start from in terms of the arrows from the diene. So I have 4 carbons, so I want to number those for my own convenience. I got 5 and 6 on the dienophile. So I start from right here. I use one of these pi bonds to attack this carbon, and then I use that pi bond that was on the dienophile to make a new bond with carbon 1 there. And then eventually this pi bond that was already between the carbon 1 and 2 is going to be moved up between carbon 2 and 3. So there is actually 3 arrows always going to be in these reactions, and you're going to be killing 2 pi bonds. So 2 pi bonds are going to be broken, or you can say killed, and then you 2 new sigma bonds are made. So that's how you want to look at it. Now, if I go ahead and put it all together now, so I'm going to go ahead and copy this down here and just keep track of your carbons there. So 1, 2, 3, 4. And then I know I also have my dienophile. I'm going to go ahead and bring that down here. And I'm going to take out one of the bonds there. So now I'm creating a new bond here between carbon 1 and 6 and between carbon 4 and 5. And then I'm going to have a pi bond recreated between 2 and 3. So you can clearly see 1, 6, and 4, 5 are the 2 sigma bonds are made, and you're breaking 2 pi bonds, and then you're reforming one of the pi bonds, but just at a different location. So this is how the Diels-Alder reactions work. And typically these reactions are reversible, and you can actually break this up and make these starting materials back at a very high temperature. So you got to be careful with the temperature conditions when you're running these reactions. If you look at the molecular orbital diagram, and these are the molecular orbitals for these pi system, and hopefully you already know all this. If you don't, you want to watch another video of mine where I have talked about how you arrange those. So this is going to be pi 1 to pi 4. That's for the diene, and for the dienophile, since you only have 2 pi bonds or 2 p orbitals, you're just going to have psi 1 and psi 2. And I got a total of 4 electrons in the diene because there's 2 pi bonds. I'll have one here, two electrons in the first set, then 2 electrons in the second set. And then I have only 2 electrons in the dienophile, so I'll have 2 electrons in the first set. So making this psi 2 as your HOMO, so that's your highest occupied molecular orbital, and making psi 2 of this dienophile as your LUMO. So that's going to be lowest unoccupied molecular orbital. So actually I have drawn this particular guy right here. So that's your psi 2. So there should be an electron transfer from the HOMO of one molecule to the LUMO of the other molecule for this to take place. So when I arrange it this way, so this is going to be the LUMO of your dienophile, and this is the HOMO of your diene. Now you can clearly see on the bottom these orbitals are matching here. So this is going to be in phase constructive interference, and this is also going to be in phase right there. So these shading orbitals and non-shading orbitals are actually matching with one another, and as a result, you create this new sigma bonds, and that makes these Diels-Alder reactions happening. So this is the orbital set. Let's talk about some of the examples, and that's obviously going to be the more important thing. So in here, I'm going to be talking about the examples that you're going to be typically seeing in sophomore organic course, but this stuff gets super complicated, and I'm not really going to be talking about anything that's going to be a graduate level course or a special topics organic chemistry course, but these are the basic things that you're going to be seeing in a sophomore organic chemistry or college level organic chemistry. So if I say in this first example, these are going to be stereospecific. So, and I'll talk about if you start out with trans, you end up having a trans. If you start out with an assist dienophile, you end up getting an assist dienophile. So in this particular case, I'll call this 1, 2, 3, 4, and then I have 5 and 6. Both of these, the diene and the dienophile, are symmetric, so I don't really have to worry about the regioselectivity here. So I know whether I have this 4 attacking the 5 or 1 attacking the 5 doesn't really make a difference. And then I can have this 6 going back to 1, and then this bond rotating, and this is how your concerted steps gonna take place. So let me just go back and copy actually this down instead of remaking it. Okay, so let me go ahead and remake one of them. So suppose this is my 6-member ring that I'm going to create, and I'm going to do a little bit of color coordination there. I'm going to go ahead and make this green because those are the new bonds. I'm going to go ahead and make this yellow, and I'm going to keep this as my reference for the next sets. So I can go ahead and number these out 1, 2, 3, 4, and then this is going to be 5 and 6. So the new pi bond is going to be between 2 and 3, and then between 5 and 6 there is carbonyl groups attached on the 6 and on the 5. So I got to put those there as well. So these carbonyl groups are actually trans with respect to one another. So they need to stay trans as well. So I can have one of them coming out of the page like this. And I can have the other one going back into the page because it's in a trance. So, and then I can also have the enantiomer of that as well. This is the possibility. So if I start out with an trance, I'm going to end up getting a trance, and that's what this theory specific really mean. What happens in the next one here? So the next one, instead of having a trans dienophile, I actually have an cis. So I want to stay cis when I'm making my product. So all I really got to do is just going to copy this down because everything else is actually the same. So I can have both of these guys either coming out of the page, or I can have both of these guys going back into the page. So if I have this coming out of the page, this has an internal plane of symmetry. And since it's got an internal plane of symmetry, one side is a mirror image of the other side. I can also have those going back into the page, but when I rotate it, it would be the same thing. So that means this is actually going to be a meso compound, so that you're going to be creating there. You don't really have to have only carbonyls. You can have also the nitriles that I have here. So for the nitriles, all I really got to do, just instead of having the carbonyls, I would go ahead and put the nitriles there. Everything else right now staying the same. So this again was a cis dienophile. You want to stay cis in the ring, so you will make a meso compound. If it's a trans, you will make a pair of enantiomers. If it's a cis, you make a meso compound because either both of them would be coming into the page, or both of those would be going back, coming out of the page. And in either case, it's actually the same thing because if you flip it by 180 degrees, you can get the other compound. Let's talk about enduros, especially whenever you have these bridges. In case of these dienes, you tend to make endo products, and how that's really going to work out. So let's say I'm going to have this attacking here right now, and this coming back here, and then this bond is moving to remake this pi bond. I can go ahead and put this down here, and now recreate your pi bond here, and then I can have these new bonds created, and I'll redraw that in a minute just as in a better structure. Let me draw that again. So I'll have 5 and 6 here. So remember, this is 1, 2, 3, 4, 5, and 6. So this is going to be your 5 and 6. And then this X right here is going to be endo. So what does that really mean? I could have either this coming down, or that's one possibility, or I could have this going up like this. So this is not very visual at this time, but if let me just try to redraw it as in a better structure. But this is how you want to redraw this. So this is 1, 2, 3, 4, and I want to go ahead and put those like this. 1, 2, 3, 4, and now I'm creating new bonds there. That's going to be 5 and 6 there. So it's 5 and that's 6. And then also remember there's a bridge to the first and the fourth carbon. There's a methylene group, so I want to go ahead and put that right here in the bridge form. And then obviously there is a double bond between the second and third. And now the question is where the X is going to be. So X is going to be any of those carbonyl substituents basically. And then that needs to be endo in a sense that when you have this X pointed down, it does a better overlapping, or also called a secondary overlapping with this pi orbital, because this X also going to have an unhybridized p orbitals, and when it has an unhybridized p orbitals, this will do a secondary overlapping with the pi bonding of carbon 2 and 3, and that makes them a more stable transition state. So this, whenever this X is pointed down or in the direction of this bigger bridge where you have a pi bond, this is called an endo product. And if it's going up like you had in the other case, that would have been exo. So how would the exo really look like if I just, draw the same type here? Then it would have been pointed up here. So then it's going to be closer to the smaller bridge that's on the top, but that doesn't even have any pi bonds for a secondary overlapping. So this is going to be exo in that case. So your endo is always going to be the major product. So make sure you know your endo rule, and it works well whenever you have these cyclic things. You will also see these whenever they are linear or open chains, but it becomes prominent whenever you have a cyclic. So this next one is going to be similar. So when I'm drawing the product, I'm just going to go ahead and copy this down. So right now it's a symmetrical. It doesn't really matter where would I put this carbon, whether I put it on the carbon 5 or carbon 6, because I can have carbon 1 attacking the carbon 6, or I can have carbon 1 attacking carbon 5. Right now, if you have any one of those dienes or dienophile to be symmetric, then it doesn't matter where you attack. But it would matter if both of them are unsymmetric. So I'll talk about that in a little bit. So then to make these endo, I would have this pointed down. So I'll have an O. So now you see here this pi bond right there, and this pi bond would be closer, and they can do the secondary overlapping that makes this transition state more stable. So that's going to be your endo rule there. Let's do a couple more examples there. So I got this next one here, and I'm just going to copy this down, and I'll erase part of it. So between 1, 2, 3, 4. On 1 and 4, you got this 2 methylene groups. So I'm going to have that something like this. So keep that in mind. And then I'm going to have this cyclic group here, and that's just going to be 5, and that's 6. So again, right now it doesn't matter where you put, whether you attach 1 to 6 or 1 to 5. And then I'm going to have this in the endo form, so I got to have this pointed down. Oxygen there, oh there, oh there. If you make those pointed up, that would have been incorrect. You want to make sure they're pointed down in the same direction where your pi bond is between carbon 2 and 3 so that they can do the overlapping better. I can also have the endo for this next one. So this next one, I don't really have a bridge structure, So it's just going to be, I'm just going to go back and copy this down maybe, and I'll erase part of it. So let me take these stuffs out. So 1, 2, 3, 4, and let's call this 5, and let's call this 6. So that's 5, and that's 6. So this is again going to be your endo. So they will be pointed down. They're going to bring back into the page like this. Because they can do the overlapping, secondary overlapping with this pi system. And then the methyl group that you have here will be going back into the page here. And I'll talk about how that goes back into the page when I talk about the stereochemistry, but right now just know that this is going to be going back into the page. Here, more or less talking about the endo rule, that this needs to be pointed down based on the endo rule. That's going to be your major product. So that's your stereospecific rule and and the endo rule. Let's talk about regioselectivity. So the regioselectivity comes into play whenever you have these dienes and dienophile unsymmetric. And let's take an example of these questions I have here. So in the first one, I have an symmetric diene, and then the dienophile is unsymmetric. So it doesn't really matter how I do the attack, whether I do, let's call this 1, 2, 3, 4, and 5, and 6, whether I do 4 attacking the 5 or 6 attacking the 1 and vice versa, it will still make the same product. And I'll show you with an example here. I'm just going to copy this down just for the sake of time. I'll bring this down here. So if I have this 1, 2, 3, 4, suppose this is going to be your 5 and this is going to be your 6. So 6 is going to have this group attached to it. So I can go ahead and make this endo if I want, or point it down. So that's one possibility. But what if I flip it where I actually attach 1 and 5? And I don't really have to worry about the stereochemistry here. And let's suppose if I don't worry about the stereochemistry and just to worry about the regioselectivity. So that's one possibility where the 6 is going to be attached to 1. The second possibility would have been, okay, let me just go ahead and duplicate that. And in this case, I'm going to be attaching a 1 with 5. So then in that case, 6 will be attached with the carbon 4. So now carbon 6 will be the one that's going to be getting the carbonyl. Now there's really not any difference between those two in terms of these regioselectivity. And that's what the regioisomers are whenever they are constitutional isomers. They becomes the regioisomers, but they're actually the same. So there's no regioselectivity if you have an asymmetric diene, and that holds true for the dienophile as well. In the second example I have here, this dienophile is actually symmetric, and this being symmetric will not affect the regioselectivity of your product here. So I could take this out. I could have this one attacking with the 6, and that's going to be going up. Or I could have the second example where you take this part out. Now this 1 is going to be attaching with the 5. So remember these 1, 2, 3, 4, 5, and 6. So in one case I have 1 attached with 6, and in the other case I have 5 attached with the 1. So in either case there's really not any difference between those two compounds. They are not regioisomers or they're not constitutional isomers. Now, the regioselectivity really takes place whenever you have these unsymmetric diene and unsymmetric dienophile, like I have in this next example. Then how does this really play out in that particular case? Now, here you got to worry a little bit about the resonance in these guys. So I know my alkyl is an electron donating group by inductive effect. So it's going to donate in the electron. So when it puts the electrons into this ring, um, this carbon, let's call this 1, 2, 3, and 4, this carbon number 4 is going to be the most electron-rich carbon, because all those electrons will be poured into this pi system having the carbon 4 with most electrons. And then what about this dienophile, how this works out? And I can go ahead and draw the resonance of that. And I'll say, okay, if I move this down here, because pi bond gets moved here, then pi bond between the carbon and oxygen breaks, and then you make a new pi bond here. Oxygen gets the negative charge, and this carbon gets the positive charge. So if I call this 5 and if I call this 6, the carbon 5 is the one that's going to be the electron poor carbon based on this resonance. As a result, once you know which one is the most rich electron rich carbon in diene, and you know which one is the most electron poor carbon in the dienophile, those are the one that's going to initiate the arrows. So I'm in this particular case, I cannot have any other initiative but 4 attacking the 5 or 4 connecting with the 5. And then after that, I can have this 6 attacking with carbon 1, and then I can move this bond right here. So let me just go ahead and copy this down here. So 4 attaching with the 5, and then let me put that away for right now. And then you have 6 is going to have a carbonyl there. So that could be in and out of the page. I'm not really worried about the stereochemistry here, but just the regioselectivity. And then this 1 is going to be also right here. So this is the only isomer you're really going to make, or this is the major one you're really going to make. The other one, where if I say I could have the 1 attached to with the 5, that would be the minor one. So let me just go ahead and draw that as well, just so that you guys can see it. So in that case, this would be 5, and this would be 6, and the 6 would have the carbonyl on this here. So I didn't really draw those in and out just because I want to show the regioselectivity there. But if I want to talk about how they would be, this carbonyl could be in and out of the page, and this methyl group will be back into the page, and I'll show you that in a minute. But this one is going to be the minor because of the regioselectivity issues there. I have this next example here. So same story, I got a lone pair of electrons on this oxygen, and if I worry about the resonance here, the previous example was with the inductive effect, and here you can see the resonance, and this comes out for right here. So if I go ahead and draw the resonance structure of that, I get a double bond here, and I got a negative charge here, and then plus I can have the same story with this CN. So remember the CN, this is how it looks like. I can move this down here and this one come up here, and the resonance of that would look like this. So if I count these carbons, 1, 2, 3, and 4, and then I got 5 and 6. So again, carbon 4 in the diene is the one that's going to be the most electron rich, and carbon 5 in the dienophile is going to be the one that's going to be the least, or is going to be the most electron poor carbon, or the carbon with the positive charge. So I'm only going to have carbon 4 and carbon 5 attaching, and when this comes back, this carbon 6 is going to be attacking carbon 1, and this is going to be remaking this double bond between, or pi bond between the second carbon and the third carbon, and this goes back onto the oxygen to restore the aromaticity. So your product here is going to look something like this. So keep track of your carbons. So 6 is going to be the one that's going to have a nitrile group, and 3 is going to be the one that's going to have the methoxy group. So this is how it's going to look like. The other isomer is not really going to be observed. This is going to be the major one. So you cannot have one connection, one connecting the 5. It's only going to be one connecting the 6 in this particular case. And you can number those however you want, but however you number those in the reactants, you want to keep those numbers to be the same in the products so that you're not really messing up the regioselectivity there. And if I want to worry about, okay, how does this bond is really gonna look like? I just drawn this in the form of a line, but remember this could be going into the page and this could be coming out of the page, just like we have said earlier when we did the stereospecificity, when we did the stereospecific reactions of those, and this could make an pair of enantiomers technically. Okay, so this is all you really need to know about this regioselectivity. Let's talk about the stereochemistry. If I have different groups on this diene, like I have X here, Y here, and A here, and B here, when this attack really takes place, it really attacks from the bottom. So when it attacks from the bottom, like this is going to attack here, this is going to come down here, and this is going to come down here. So when that happens, this Y actually gets rotated to come on the top, and this X goes behind the wall. So that's how it's going to look like. So if I go ahead and draw this out, let me just erase all of those. So I know this is 1, 2, 3, 4, and the new bond is going to be made between 1 and 2, 2 and 3, and on 1, whichever was at the Y location is going to be coming out of the page like this, and whichever group was on the X location would be going back into the page. So this is something you just probably want to memorize, that this is how it really works for the sophomore organic chemistry course. And then this A is going to be going back into the page, and then this B is going to be coming out of the page. So that's going to be your stereochemistry, and let's look at a couple of examples here. So I have this symmetric diene, so I don't really worry about this regioselectivity. I'm just going to go ahead and copy this down and put it right here. And then I see here, I'm just going to take these scripts out and remake those. So I can clearly see that this methyl group is cis with respect to that particular double bond. And if I compare that, it's going to be at the location of a Y in the previous example. So that means that must be coming out of the page based on what we just learned. And then this other group that I have here, this methoxy group, is trans to that double bond. And if I go back and look at my reference, it's at the same position where A was, and A would be going back into the page. So this would be going back into the page. So this is how it's really going to look like in terms of the stereochemistry. If I have, suppose, another example here, and I can go ahead and maybe copy this down. Maybe you want to try to do this on your own and see if you get the right answer. Oh, there shouldn't be any Y here, just the methyl group. Let's call this 1, 2, 3, 4. This is 5 and 6. So I'm going to have this as an endo form, so that means they will be going back into the page like this. All right, and that would be making the remaining groups that's on that 5 and 6 to be coming out of the page, and that leaves you actually with only hydrogens there. So your hydrogens would be coming out of the page. And I didn't really change the position of this methyl group and this methoxy group because they were actually very similar to what we have in the previous example. So this methyl group was coming out of the page, and this methoxy group is going back into the page. If I want to go ahead and redraw this actually, I would, let me just copy this down. I can go ahead and just draw them in the plane like this and just show those better. I know at 5 and 6 these hydrogens will be coming out of the page. So I can have the hydrogens coming out of the page, and that automatically tells you that these carbonyl groups will be going back into the page. So that's another way of drawing this, but either way would be fine. We have another example here. It's very similar again. So this is indeed in the cis form for the dienophile. So let me go ahead and copy this down. So I'm not really going to change the location of this methyl at carbon 1 and the methoxy at carbon 4 because carbon 1 methyl is coming out of the page based on the reference, and this 4 is going to be going back into the page. And then I got this 5 and 6, so this is symmetrical. So this is a cis form rather, and I don't really have any pi bonds or any secondary overlapping that could take place on this dienophile. As a result, I could have these either coming out of the page or I could have those going back into the page. So either way, that would work. So I could also have, but they both need to be cis to one another. They can't be trans. And now in this case, I'm not really saying that they're going to be meso because the diene that we used wasn't symmetrical, so there's no plane of symmetry in this particular case here. So they could be called in a pair of diastereomers. Okay, let's talk about this last example I have. So this is, you got to worry about the regioselectivity, and then you also got to worry about the stereochemistry here. I would say this is going to be 1, 2, 3, and 4. And I can clearly see that this lone pair will go in there and this pi bond will break out to make sure that carbon 4 gets the most electron density in this particular case here. So I'm going to go ahead and put a double bond there, raise one of the lone pairs, positive charge on the oxygen, and a lone pair of carbon with a negative charge on carbon number 4. And then I got this guy right there with the resonance. So remember this CN. It can move down here and that can move up. So negative charge there and a positive charge there. So if I call this 5 and call this 6, and so this would have been 5 and this would have been 6. So now I got to worry about which carbon this carbon 4 is really going to attach it to. Is it going to attach to carbon 5 or carbon 6? So based on the resonance of how we have drawn here and how we have numbered here, carbon 4 must be attached to carbon 6, and that's going to be your regioselectivity there. So I can go ahead and flip this. When I flip it, oops, double bond there and there. So this is going to be your 5 and this is going to be your 6. So I got to have negative there, 4 attacking the 6, and then when this comes back, this attacks right there, and this comes out here. So then, let me just copy this down, and I will raise the side chains on it and redraw those so that you guys can see what's going on. If you number those, it will make your life a lot easier. So 1, 2, 3, 4. And now I know 4 is attaching to 6. I'm going to call this 6 here. 5 is attaching to 1. Call this 5. Now start with carbon 1. Carbon 1 has a methyl group. That methyl group, based on the reference, if you go back and check here, based on this Y, would be coming out of the page. I'm going to go ahead and draw the methyl group coming out of the page. And then this methoxy group on carbon number 3 is really not gonna do any stereochemistry or show any stereochemistry because it's at the double bonded carbon, so that stays as it is. There's nothing on carbon 4. Not sure why I called this 3, but this would have been 4. Nothing on carbon 4, so you leave that as it is. So carbon 6 has nothing again, and carbon 5 has an nitrile group. So this needs to be an endo with respect to, according to the rule, because remember this nitrile also have a double bond. So if it's going back into the page or pointed down, or another way of saying, if I, momentarily draw this kind of pointed down, I can't really draw this on here, but if this was drawn something like this, where this is 2, 3, and then I have 1 here, 4 here. So at 5, I want to draw the nitrile grip pointed down so that I can have this secondary overlapping with the pi bonds or unhybridized p orbitals. So the only way you can get that if this is going to be going back into the page. So that's something you got to be really, really careful. So here we have to worry about the stereochemistry. We have to worry about the selectivity. So you will see some questions where you have to worry about both, and some questions you may have to just worry about one, either the stereochemistry or the selectivity. So this is how you're going to be doing all these Diels-Alder reactions. If you have any questions, feel free to leave any comments in the section below.